on this graph, does conc H2A ever go to, or does the fraction of H2A ever equal 1? It's always something slightly less than 1, right? And you look at your expression for this term, conc H2A, and you end up with conc H3O plus, a term conc H3O plus over conc H3O plus squared, which if these terms didn't exist, would go to 1 at some point, as H3O plus went to 0. But you've got that Ka1 times Ka2, so there's always something in the denominator extra that's kind of decreasing that amount relative to 1. So you see that even at low pH, conc H2A never ends up being equal to 1. So drop the pH as far as you want, you're never going to get just completely protonated H2A. There's always going to be some equilibrium amount of the other species in that solution, right? Concentration of HA, not as much to say about it, but concentration of A2 minus, if you go to high pH, where you get low concentration of H3O plus, you end up getting the ratio of Ka1 times Ka2 over Ka1 times Ka2 in the event that H3O plus, conc H3O plus goes to 0 high pH. And so this concentration begins to approach 1, but just like H2A never went all the way to 1 at low pH, conc A minus never goes all the way to 1 at high pH. It tops out somewhere just below 1. So you plot all of these fractions on a graph relative to each other. You see that at some point, when you get to pH is equal to pKa1, the concentration of H2A is equal to concentration of HA minus. Anywhere below that in pH, species H2A dominates. Between pKa1 and pKa2, species HA dominates. And then once pH is larger than pKa2, species A minus ends up dominating. At pH is equal to pKa2, the concentrations of HA minus and A minus end up being equal. So take as many protons as you want on an acid. This is a diprotic acid. You can do the same thing for a triprotic acid, write out all the concentrations, and you're going to get that same kind of alternating concentration effect as you move through the various pKa's for the species. Yeah.
So you're more interested in having us know what happens with the liquid chart, on H2A?
Honestly, I'm interested in you guys knowing that as concentration builds up in the solution, that shielding effects lower the chemical potential of the ion in solution.
Okay.
That's the thermodynamics I'm concerned about.
Okay.
I'm only showing you this stuff because I would feel bad if I didn't, but honestly, this is Gen Chem. This is stuff that you guys theoretically have already seen, you already know. The only reason I'm reviewing it is because I'd feel guilty if I didn't. Okay. So this is just, refresher from Gen Chem. Right? I mean, in terms of thermodynamics, I want you guys to understand the approximations. It's always, when you're taking Gen Chem and they tell you that the delta G goes as the concentrations, and you wonder why that's the case. I want you guys to leave this class knowing why it's the case, why we can express the chemical potentials as a function of concentrations. And I want you to know that it's not necessarily a safe thing to do because chemical potential is not just a linear function of concentration. This is all just review. I want you to be able to use ice tables. You guys saw that ice table that we had for the ammonia reaction where you ended up with those all those crazy algebraic manipulations. I'm not going to give you anything like that, but an acid-base equilibria would be a nice just proof that you guys are capable of running the ice tables and looking at the equilibrium constants and figuring out what equilibrium concentrations of different species are. All right, so The next little piece of math addresses the question, what if you have salt of a diprotic acid? So you've got something like H2A, but you've fully deprotonated one of the protons and you've substituted the sodium. So now you've got NaHA. You dump this thing in solution. You dump it in solution, essentially what you've done is you've added a bunch of HA minus, and you know that HA minus can either pick up protons or can kick off protons. How do you estimate what the pH is going to be in a situation like that? And this is a pretty crazy little piece of math that requires that you make some assumptions that are only true in certain conditions, but we'll look at it and address what those conditions are. So we draw out our ice table, and we draw all the different species. We've got more species in this ice table than the other one. We've got HA minus, which is what we initially dumped in solution. So we'll write it out as conc initial, conc salt initial. Conc H2A initial is 0, conc A2 minus is 0. None of those have been created yet, and H3O plus concentration is 0. We throw that guy into solution, and some of it deprotonates, causing H2A to increase by an amount X. Some of it deprotonates, causing conc A2 minus to increase by an amount Y. Our concentration of H3O plus ends up being Y minus X. We write out the initial, their equilibrium concentrations. We've got conc H2A is X. Conc HA minus is whatever that initial concentration was, minus X minus Y. Conc A2 minus at equilibrium is Y, and conc H3O plus is Y minus X. We can then write out Ka1 and Ka2 in terms of those equilibrium concentrations, and we get the two expressions on the right-hand side of the screen. Multiply those two expressions together, and the terms for conc HA minus end up canceling out, and you get that Ka1 times Ka2 is equal to Y minus X squared over, or times Y over X. Conc Y minus X is conc H3O plus, or was defined in our ice table, and so we get that Ka1 times Ka2 is conc H3O plus squared over, or times Y over X. What we're going to do now is we're going to just write that out. We're going to write out Ka1 and as a function of Y and X and the conc initials, the concs and the salt initial, and we get this expression, X times Ka1. So we're taking this top expression and we're moving the X over and multiplying it by Ka1. We're left with Y minus X times conc salt initial minus Y minus X. This whole guy, after you multiply everything through, ends up giving you this big, long term where you have powers of Y squared, X squared, you've got X times Ka1, and then you've got these terms where you have the initial salt concentration times Y and the initial salt concentration times X. So this is just a kind of rewrite of the expression for Ka1. We're interested in Ka1 because ultimately that's going to allow us to obtain conc H3O plus. In the event that you've got a large concentration of salt, that you've dumped in a ton of the salt, what will happen is that these terms, the Y squared terms, the X squared terms, the X times Ka1 terms, will end up being very small relative to the terms that contain the initial concentration of the salt. And so you can just get rid of those terms. You can approximate them as being 0. And this leads to the approximation that Y over X is equal to 1. You take that approximation, Y over X is equal to 1, and that gives you that this is equal to 1, therefore conc H3O plus is going to be the square root of Ka1 times Ka2. or KH3O plus is the square root of Ka1 times Ka2. You take the log of both sides of that, take the negative log of both sides of that, and you end up with an expression that the pH is equal to 1/2 pKa1 plus pKa2. So you've seen that expression before for an amphiprotic system. You can approximate the pH as being kind of an average of the two pKa's. And so depending on what those two pKa's are, you might have a slightly acidic or slightly basic solution, but plug in those pKa's and find out. Again, that only applies if you have high concentrations of salt. If you have low concentrations of salt, then you can't make those approximations, and you'll have to do a little bit more rigorous math. So what happens if you stick a salt in a solution? So it's not necessarily an acid, it's not a base, it's a salt, but it's composed of species that can behave as acids or can behave as bases. Your book gives you a couple of examples. It gives you an ammonium chloride salt solution, and it gives you a sodium acetate salt solution. And basically, you need to be able to, for these salt solutions, you need to be able to look at the components that are going into solution and ask yourself or tell yourself which of those components are going to actually affect the acidity or basicity of the solution. In general, ions like sodium and chlorine don't alter the pH of the solution much. They can do it slightly. Some negatively charged ions coordinate with water and cause water to lose a proton. Not a lot of the positive charged ions affect acidity very much. But species like NH4+, NH4+ is the conjugate acid of a weak base. And so you've got NH4+ in solution, that thing's going to start kicking off protons. So you look at the concentration of your salt, you turn that into a concentration of NH4+ initial, you use the pKa of that conjugate acid of the weak base, you draw out your ice table, and you answer the question, how much H plus does NH4+ kick off in the solution? So, solution of ammonium chloride, figure out what the concentration of ammonium chloride is, set that equal to concentration of ammonium acid or ammonium ion, draw out your ice table, figure out what your pKa is, and proceed as usual. Right? Sodium acetate. Dump that stuff in the solution, you're going to have a high concentration of this of that weak base acetate ion, and so basically proceed the same way, except now you're assuming that acetate is a weak base. Draw out your ice table, figure out what your initial concentration of acetate ion is, figure out what your pKb for that species is, determine equilibrium concentrations, and determine pH that way. Right? So whenever you have a salt in solution, look at the ions that are present in that salt, figure out whether or not any of those ions are going to end up acting as acids or bases. If you've got a combination, you've got a salt that's got a weak base and a weak acid, then you're going to have to do an ice table for both of those. See how much H plus, the weak acid, kicks out in solution, see how much OH minus, the weak base, puts in solution, adjust the amounts to figure out what the total concentration of H plus and OH minus is, right? It's not Hasselhoff.
It's Hasselhoff.
Yeah, but I like Hasselhoff. I've been saying it that way for a long time. So we're just gonna look at this derivation of the Hasselhoff equation. You guys have probably seen this before. It's just kind of a tidy way of looking at how pH is affected by the relative concentrations of the acid and the conjugate base for one of these systems. The way that we obtain the Hassel-Bach equation is that we write out the K for the acid in terms of conc HA, conc A minus, conc H3O plus, and then we isolate conc H3O minus. It ends up being Ka times conc HA over conc A minus, and we take the log of both sides. You take the log of both sides, you get log H3O plus is equal to log Ka plus the log of the ratio of HA over A minus. We know that log H3O plus is negative pH,